Um, yeah. Okay, so I guess today we'll do spectral analysis of undirected random walk. Mukul actually said something kind of interesting to me today. He said he was stressed out by the last chapter, I guess, when he was reading it, which I was like, oh God, am I writing that bad? But he made this point that, oh, we've learned all this kind of mathematical machinery, but at some level it's not fully connected yet. It feels a little bit magical at certain points, maybe some stuff like this. So, for what it's worth, we're going to keep working on some of the ideas this week. So I'm hoping that maybe the lack of motivation in his words was not so much like the application. Applications were fine, like doing connectivity in log space is kind of cool. I think he just means it didn't feel like we had the complete story mathematically yet. We had learned some tools, but we're kind of floating out there. So I'm hoping as we add more this week, doing more stuff related to matrices and stuff like this, you'll see more connections and it'll become a little bit more of a compact idea. So in that different sense, hopefully things will be a little bit better motivated. So, well, whatever. That's just a big word salad. Let's just see where we go. Okay, so at the beginning of this kind of linear algebra theme, we first did page rank, which was also about the existence of a stationary distribution for any random walk. And really, this had to say something of this was an eigenvector, ultimately the random walk matrix, but in a very special way. It turns out that a random walk matrix, because all the coefficients are non-negative, essentially, you can use this very strong theorem called the Perron-Frobenius theorem, which is much stronger than the usual fact that every matrix has an eigenvector. Because it tells you that there's going to be some like eigenvector with the biggest possible eigenvalue, and it's going to be positive. And for a random walk, it'll be 1. And that eigenvector will be all positive coordinates, no complex values. Like if you're not careful, you're going to get complex values. You wouldn't know what to do with them, right? But the fact that you're getting sort of this dominant eigenvalue that's real valued and positive, and an eigenvector that goes with it where everything is positive, okay, that kind of maps to a distribution. That's something very convenient. So that's very special is the point I want to make. Somewhere lost in maybe all the proving we did is the fact that, oh, this is a very special situation where you get something very, very nice. And then last time we're talking about random walks again, but this time for a different application. This was the idea of trying to figure out if a graph is connected, but doing it so very little space. And the nice thing about random walks is that it takes very little space to run it, because all you need to do is remember where you are in the graph. So just the name of a vertex is like log n bits. In our algorithm, we counted how many steps because maybe you give up after a while. That's another counter. Okay, so it's just 2 counters. And what was kind of cool was to show. So what we showed is that in I think mn steps, if I remember correctly, you expect actually to start from any vertex to visit everyone else in the graph. In fact, sort of following the path of some spanning tree thingy. Uh, and so we're able to analyze things like the cover time and the hitting time of a random walk, sort of in the worst case, no matter how weird the graph looks, right? And to prove it, we took this crazy detour through electrical networks, and it's still a little bit magical to me how uh, it's certainly a very nice trick proof. I doubt like the cover times and hitting times were originally proven this way. It's probably proven more directly, but this is sort of this nice connection. But I like the one we did last time, even though it's a little magical, because it also introduced us to things like the Laplacian and thinking about the graph from a matrix point of view, which we're going to do more of today. Okay, so right, so today we're going to talk about the spectral theorem for symmetric matrices, and then we're going to use that to discuss random walks and get very kind of refined theorems, much more um, detail, much more informative than what we did last Tuesday, which was just existence of a stationary distribution. Okay, so right, so a few lectures ago, we proved this, right? We showed that any directed graph um, uh, has a stationary distribution that corresponds to an eigenvector with eigenvalue 1. It's unique, all these things if the graph is strongly connected, right? That turned out to really just be the Perron-Frobenius theorem. So today what we're going to show is the following. Maybe I should have covered it up, but oh well. Okay, so we actually know from the Perron-Frobenius theorem that the random matrix R, we know a bit about its eigenvalues, right? Because we know 1 was the biggest eigenvalue in absolute magnitude. So all the other eigenvalues are between strictly less than 1 and greater than or equal to -1. Okay, so we actually know we've kind of contained all the eigenvalues, sometimes called the spectrum of the matrix. Now, okay, it is true that mu n could be all the way down to -1, but imagine there's some gap between that and -1. Okay, so let's look at gamma, which will be 1 minus the maximum mu2 or absolute value of mu n. Okay, absolute value. That means it could be close to 1 because it could mu n could be close to -1. Okay, but let's say there's some gap there. Okay. Now, what's this theorem saying? This theorem is saying, okay, if I start at any distribution x, okay, and I apply a random walk a bunch of times, and then S is representing my stationary distribution. And this is like, I think, the L2 norm. Okay. So on the left, I'm saying, look, after I take k steps, how far am I from the stationary distribution? So last week, we only showed there exists a stationary distribution. Here, we're trying to actually measure how far away I am from the stationary distribution, at least an L2 norm. Okay. And it says, okay, this difference is at most some polynomial term here, but 1 minus gamma to the k. Okay, so what does that mean? That means if there's like a constant here, if gamma is like 0.01, okay, then you're getting like 0.99 to the k. So you're actually going down exponentially fast. Okay, so what's this saying? It's somehow saying, look, if you study the eigenvalues, and if there's this gap between the first eigenvalue and sort of the second largest eigenvalue in absolute value, that's usually either mu2 or negative mu n. If there's any constant gap there, then random walks will converge very fast. Okay, so that's much stronger than just saying there exists a stationary one. It says, oh, you can actually converge to it very fast. Yeah.
Stationary distribution is just like the probability of being at some vertex, or I guess every vertex.
So stationary distribution is that unique distribution over the vertices, or if you took a random walk from this stationary distribution, you still be at the same stationary distribution. If I start at a particular vertex x and I start walking around, you might wonder if you start to approach a stationary distribution. In fact, it's not obvious that you will always approach a stationary distribution. If you just have one edge and you start on one side, you just go back and forth, back and forth, back and forth, and you're never at the stationary distribution, which is 1/2, 1/2. So somehow that must be ruled out by this eigenvalue condition. Okay. Yeah. Absolute value of, well, I guess it should have been mu n. I got my mu's mixed up with my u's. Okay, unfortunately, that is probably going to be copy and pasted all over the slides. Okay, but so this is very I don't know if you haven't seen this before, it might be kind of surprising because it's saying, look, something to do with eigenvalues is governing how fast you converge to stationary distribution. Yeah. Oh, yeah, that's not really described. That's the maximum weighted degree and the minimum weighted degree in the graph. Weighted degree of any vertex and a minimum weighted degree of any vertex. Yeah, these are sort of low order terms at this point. Yeah, unweighted graphs, so that would be like most n or something. All right. Any other questions? Yeah.
Is this how to duplicate?
Uh, yeah, I think in the worst case it is tight. Yeah. At least up to certain. If you want to go lower order terms or something, then okay. This is also a primary way to analyze random walks, so it's a good. Okay. Any questions? All right. So the question is, how do we actually prove this? Okay. So we got to discuss a little bit the spectral theorem for symmetric maps. Okay, so I guess our main working example for symmetric matrices. So given a graph G, what you saw last time is that you can model it with some kind of symmetric graph, a matrix called the Laplacian. Last time the Laplacian kind of arose out of electrical potentials, like it came at the end. I'm going to reintroduce it where it kind of comes at the beginning. So I'm going to define it in terms of a sum of rank 1 matrices. But this kind of U outer product V, that's also the same as U V transpose, but I hate transpose stuff. So one way to define the outer product is something like this. if you're kind of looking at what X, you, whatever, you'll get something like this. Okay. So that's defines it, clearly. So as a matrix, if you like matrix forms, I don't, uh, U outer transpose V will look like this kind of crazy thing. Okay. And if you like identities, then for example, so if I look at like three linear maps, so this is a rank one map, right? Going from whatever space this lives in to whatever space this lives in. Okay. If I look at kind of applying A to the output of U outer product V to the output of B, right? Combining those three linear maps, then you get something like this. Okay, you'll get the same rank one map with AU and BV. Or if you want to, for example, say, okay, I have one rank one linear map and I apply another rank one linear map. What does the combination look like? Anyone want to shoot for it? It'll come out like this. Ultimately, you're going from Y space to U space, basically. So it's the only kind of thing that makes sense. And these are also living the same space. So, okay. You can go through this most slowly to verify it, but okay. But okay, so anyway, the Laplacian of a single edge will be, if I look at this 1u minus 1v, that's some kind of notation. I'm just saying, imagine a vector that's all zeros everywhere, but there's only a 1 for the uth coordinate. And then 1v will be all zeros, but 1 for the vth coordinate. Okay? And it's going to be outer product of this thing with itself. Okay? So for example, if you apply it to some vector x, this is indexed by vertices. Okay, so x will be an RV. What will be this thing? Just to go through the definition slowly. So what would 1u minus 1v comma x be like?
1x minus 1v.
Xu minus xv? And this is just kind of doing it to both sides. Okay, so you get something like this. Okay, so you have some edge, and you have two values on the endpoints, and you look at their sum, their difference squared. Okay, so that would be the Laplacian of a single edge. Okay, and the Laplacian of a full graph will just be like the weighted sum of those individual small matrices, those individual rank one terms. You have all these rank one terms, each representing one edge, and the weighted combination will let you model the whole graph. So for example, if I now do XLX, where L is for the whole graph, what does this start to look like? Okay, so you're going to be summing up all the edges, right? And then what will a term for a particular edge look like? Yeah, yeah, something like this. So it's just going to be summing up all the differences over all the edges, times the weights of the edges. Okay, don't get too excited about the linear algebra. Okay, so Laplacian is going to be for us like a canonical example of a positive semi-definite matrix. Does anyone know what are the defining features of a positive semi-definite matrix?
For any non-zero well, for any vector, you have x transpose the x is started with 0, and it has to be a symmetric matrix, otherwise
Perfect. So the second that'll put you first said this, right? Xax is always greater than or equal to 0, and it's also symmetric. Okay, and that's the case of the Laplacian, right? So the Laplacian, because it's always a sum of differences squared, it always comes out positive or non-negative because the sum of squares, you can't get a negative number. Okay, and it's symmetric, which you can just see from one edge, and you have a bunch of symmetric things being added up. Okay, all right. When this inequality is strict, then it's called positive definite. That also means it's invertible. Okay, good. Sorry, I'm a little nasally today. Okay, so anyway, so I guess a week ago, we talked a little bit about eigenvalues and eigenvectors, right? X is equal to lambda x. So x goes in, it comes out in the same direction, stretched out, maybe flip directions, but okay. And we know that every linear map always has some complex eigenvalue and eigenvector. Okay, so when a matrix is symmetric, we can say something much stronger. Okay, so let L be a symmetric matrix. Okay, and then look at this optimization problem. I'm going to maximize XLX over all unit directions. Okay, so I want to maximize XLX over all units. This is like a geometric thing, right? Find the thing that maximizes this thing. Okay. Um, what do we know about X? Anyone want to guess? Yeah, it's the eigenvector. Uh, it, and so in fact, you're going to get Lx is equal to mu x, where the scalar is exactly this XLX value. Okay. I guess we won't show it yet, but we'll actually eventually show that it's even the biggest eigenvalue. Okay. But this is very nice. You know, if I feel like if you go back to our proof of the complex eigenvalue, and or if you want to do your determinant version, at some level that's sort of an algebraic proof, right? Because you get some linear dependency, and then you have to apply some fundamental theorem of algebra, right? There's some over constraint situation going on. But this is at some level not going to be an algebraic or kind of incidence kind of proof. It's going to be a geometric proof. It's going to be an optimization thing. That slight distinction makes sense. Okay. So in some sense, I find, the eigenvalues and eigenvectors of a symmetric matrix to be much more intuitive, much more natural, right? Because at some level, this eigenvector tells you something about L. It's kind of, you just want to maximize this thing, right? And then we'll expand on this in a moment. So, all right, so let's try to prove this, okay? And what we're going to actually end up doing is spending most of our time on this claim, but we'll go through why it's useful first. Okay, so the first claim is that take any, say, direction u that's orthogonal to x. Okay, so that means the inner product was x is 0. The claim is that u is also going to be orthogonal to Lx. That's going to be the key technical claim, at least of our proof. Okay, but let me go through maybe first why that might be helpful. Okay, so suppose this claim is true. Okay, so good. All right, so my claim is that Lx has to be in the span of x. Why? Yeah. Yeah, somehow you play the orthogonality off of each other. So if Lx was not in the span of x, if Lx was partly in x, but there's some other junk, that other junk in that orthogonal subspace would be the u that gives you some issues, right? So, right. So you have some direction x, and we're claiming that Lx has to be somewhere along this line, because if Lx somehow jutted off like this, then if I'm drawing the 90-degree correctly, this part here, this u would give you some issues in that orthogonal subspace. Okay. All right. So Lx is spanned by x, and that tells us that Lx is equal to some multiple times x. Okay. And I think if you just plug that in, so you know that x is a unit direction, so mu1 is equal to mu1 xx, and then you know that mu x is equal to Lx, so that's xLx. So after that, everything just kind of nicely matches. Okay. So if we can just show that sort of, every vector that's orthogonal to x is orthogonal to Lx, then we're done. Okay, so, all right, how do we show this? All right, this part's a little bit more analytical. So at some level, x maximizes this xlx over all unit vectors, right? So noting that that u is orthogonal, so you can also think of this as x plus epsilon u squared or something. Okay. So okay. Now, since x maximizes xlx, or I can think of that as maximizing xlx over the length of x squared if I kind of remove the normalization. But the point is, if I adjust x a little bit, you shouldn't get anything better, right? Because x is supposed to be the best. So what does f of epsilon represent? It represents like, okay, let me go from x and shift a little bit in the epsilon direction. In the u direction by small epsilon. And then the 1 plus epsilon squared just renormalizes it so that you're still working with a unit vector. Okay. So if x is really maximizing, this xlx stuff over unit vectors, what should maximize f? 0, because that will get you back to the thing, right? So this is maximized. I hope I didn't write anything. I didn't. Okay. This is maximized at epsilon is equal to 0. Okay. Which means that what do I know about f prime of epsilon? Is equal to 0. Okay. Now, okay. So sorry. F volume of 0 is 0. Okay. Now, okay. So we know that some level this thing shouldn't grow. Now, okay. So let's expand out. So the denominator grows like 1 plus epsilon. Well, okay, it grows like 1 plus epsilon squared. Okay, that's not so interesting, right? But let's look at the numerator. The numerator, I'm going to give slightly sketchy proof, is xlx plus 2 epsilon u lx. Okay, plus epsilon squared u lu. Okay, but here's what I want to highlight. Suppose by contradiction this is not equal to 0. Okay, so at some level this is growing like, so this is xlx. If I just treat that as a constant plus big O of epsilon. Okay, so this is some term, but think of this just as a constant. If I increase epsilon by 0.1, the numerator is gonna go up by 0.1 times that constant. It's gonna dominate the epsilon squared term, which is also positive anyway. Okay, but it's changing linearly. Okay, but the denominator is growing quadratically. Okay, so the numerator is growing linearly. It's adding some order of epsilon. The denominator is growing quadratically. So what does that? Why is that an issue? So if I choose epsilon to be really, really small, does the numerator or denominator grow more? The numerator is going to grow in the order of epsilon. Yeah? So you're going to get bigger. So as soon as this thing becomes non-zero, the numerator will grow faster into infinitesimally than the denominator, and that'll be your issue. Okay. All right. Any questions? Yeah. Okay, you can do the calculus. If you really want, you can expand out what f prime 0 is, and then you also get u out of u equals 0. Okay. But all that really matters is that cross term gives you this linear thing. Okay, so good. I think maybe the only important thing to look back on. So what's nice about this proof is that you're just studying first order optimality conditions, right? Because the eigenvector is coming out as such a simple uh, optimization problem that you can just write it down, look at what the first order conditions tell you. Well, you're not supposed to be able to improve your solution if you go this way or that way or this way or that way, and everything just falls down. Okay. All right. So good. All right. So at some level, you can pull out this one eigenvalue in a much more, I think, direct fashion. At some level, we didn't even really come up with an algorithm for pulling out the first eigenvector before. We just showed, okay, fundamental theorem of algebra, there has to be a zero, so something exists. Yeah. Okay, so good. All right, so that's just for one eigenvalue. And now we're going to talk about the spectral theorem, okay? Which is going to tell us a lot more than just one eigenvalue. So what does this world famous spectral theorem say? Okay, so if I give you a symmetric matrix, okay, then you can write L first as a sum of rank 1 terms, okay? So you have these n vectors, v1 to vn, they're all normalized. It'll be lambda 1, v1 outer product v1, lambda 2, v2 outer product v2, lambda 3, so forth, lambda n vn outer product vn, okay? Now there's 2 points that are very important. One is that all the lambda i's are real valued. I forgot to stress this on the previous lemma, but because the eigenvalue came out of an optimization problem like that, it's always real valued. That's always very nice.
That's because L is symmetric.
Sorry?
Because we know L is a symmetric matrix, so that automatically implies that all eigenvalues are real.
Yeah, I guess so. Well, that's the only property I used. Yeah, yeah. Okay, but now, okay. But look, the very nice thing is that the v1 through vn's are orthonormal. So they're sort of like some coordinate system. There's n directions out there, unknown, v1 through vn, but they're orthonormal, right? They're x, y, z, but it's pointed in some mysterious direction. And then, in the first direction, it's sort of acting like a scalar of lambda 1. We'll work through this in a moment. In the second direction, it's like a scalar of lambda 2, and so forth. Yeah. Orthonormal means they're all unit vectors, and they're mutually perpendicular. So that means that v1 comma v2 is equal to 0. So just like whenever we do like physics, you imagine xy coordinates, you imagine them being perpendicular. Right? But in principle, you can have any basis that they're independent. It's just most natural and convenient when they're orthogonal. Okay. So let me okay, maybe let me skip the proof for a moment. We'll come back to it, but try to explain why this is so nice first. Okay. So if you have this representation, remember, a matrix usually as given is a big mumble jumble of n squared numbers, right? With no structure. And this is saying, okay, somehow there's n secret principal directions with these nice eigenvalues. And let's see why this is useful, why it says it's not just a mumble jumble of numbers. Okay. So let's say I have some particular vector x I want to apply it to. So I start with any vector x, and I can write x in the coordinate system of those n directions. Okay? I mean, it's not surprising that if I pick any x, y, z coordinates, you can kind of figure out how you're located related to those coordinates, right? With some calculations and stuff. But to get it explicitly, alpha I is going to be exactly the inner product of x and vi for each I. Okay? So this is writing x in the coordinate system that's sort of native to this underlying matrix. Any coordinate system, you can always express a vector in it. Okay? And let's see what L does to this vector, especially if I think of it in terms of its native coordinates. So, okay, so just substituting in. right? This big lambda expression. Okay, and now let's just apply each of these terms. So this is just what the outer product does. You're going to take the dot product v1x, and it's going to go out in the direction of v1. This will take the dot product of vn and x and go out in the direction of vn. Okay, so x, and it's going to go out. Okay, and that's just getting you back the original coordinates. Okay, now if you were just thinking in terms of v1 through vn the whole time, then maybe x would just natively been given to you as alpha 1 through alpha n, right? If v1 and vn kind of coincided with like our standard basis or whatever. So in terms of these negative coordinates, what does L sort of act like? Yeah, like a diagonal matrix, right? Saying, oh, just take the first coordinate, stretch it by lambda 1. Take the second coordinate, stretch it by lambda 2. Take the third coordinate, stretch it by lambda 3. Take the nth coordinate, stretch it by lambda n. Okay, so every symmetric matrix is implicitly a diagonal matrix. There's nothing complex about a diagonal matrix. Everything you know about math goes so easily for a diagonal matrix. You know how to add them, you know how to multiply them, you know how to scale them. You can do whatever you want with a diagonal matrix. They're not like real numbers. Okay. The only tricky thing is that whatever underlying rotation may not be convenient, and maybe take some effort to compute the rotation, things like this. But there is some perspective by which any symmetric matrix basically becomes trivial. That's always there. In fact, the only hard thing about them is that what happens when you have two symmetric matrices? It is true that they're both diagonalizable. But for example, with two diagonal matrices, A times B is equal to B times A. But in general, for two symmetrical matrices, you don't necessarily have A, B is equal to B, A. But they're both diagonalizable. So what's going on?
There's some like transformation that you're applying with first transformation, and then it's the diagonal matrix that they have like said that.
Yeah, so maybe that's what you meant, but I think the most direct thing is that they are both diagonalizable, but that basis is different. That coordinate system for each one is different. So they're not simultaneously diagonalizable. That's why they don't commute. Okay, and so operator theory is just all about basically dealing with this. Okay, so that's why the spectral theorem is so powerful. Because it's saying the symmetrical matrices are about as straightforward as diagonal matrices. And this is great because our favorite way to model graphs in a matrix is also a symmetric matrix, right? So we're about to unlock something very useful for analyzing graphs. Okay, so let's go back to actually proving this. Hopefully, it's better motivated now. Okay, so we're going to try to prove this just by induction on the n. What's the base case? All right, what's an easier base case? Okay, which is the n equals 0. Not much to do there. Not much for n equals 1, but I'm very lazy. Okay, so in a general case, n is bigger than 0. Okay. All right. Now, starting from some general n, we can apply that theorem from before to get one eigenvector and one eigenvalue. Right? We know how to get one. And now the question is somehow, how do I do the inductive step? Any ideas?
Extend it to what's a normal basis or like often.
Yeah, kinda. Yeah, so I think that's maybe implicitly what we were going to do. So here's what I'm going to do. I'm going to, at some level, subtract out this part. I probably should have wrote mu1 and v1. Or, yeah, maybe mu1, v1 or something. And I'll subtract out this part and kind of look at the rest. Okay? And I also want to look at, right now this is still living in Rn, Rn. And what I want to do is I want to live in an m-1 dimensional subspace so I can properly use induction. Okay? So what I want to do, I mean, in hindsight, this is kind of like guessable because we're expecting an orthonormal basis. So I don't know if this is a great proof if you're doing it for the first time. But let's let Y be the subspace that's orthonormal to our first eigenvector. Right? If the spectral theorem is correct, and this is sort of a natural step to do because your remaining eigenvectors should all be orthonormal and living in a space, and if we subtract out this first term, we should get the remaining terms. Right? So at least in hindsight, this is a natural approach. Okay. So the claim is that B is mapping Y into Y. Right? If that's true, then I can do induction on B inside Y, because now I have an n-1 dimensional subspace. Okay, but first I need to show that B is keeping Y inside Y. It's not going outside, or else you got a big mess. Okay. All right, so I think there's not too much magic here. We just got to do it. All right, who wants to try this? I guess we can start with let Y and Y. That means that V1 Y is equal to 0. I don't know why there's a 1 here. Right?
Should that be enough?
Of course. All right, so let's just start seeing what happens when we apply B to it, right? All right. V1 By. All right, what should we do next?
Substitute the definition.
All right, let's just substitute. I don't think there's any tricks in this proof. I hope there's no tricks, 'cause I don't remember any. Okay, something like this. Sorry. Okay, so this term will cancel. This will go to 0. Well, maybe no, let me just do it slowly. So someone said linearity, V1 AY minus mu1 V1Y V1, and this will go to 0. Okay. And then what do we have here? Sorry. Okay, so that second term will go to 0 because Y is orthogonal to V1. Oh, okay, it's symmetric. So I can take the transpose without actually having to write a T. Now V1 is the eigenvalue. And then V1 is orthogonal to Y. Okay, so it's kind of straightforward. Okay, but now that you have that, by induction, you can get an orthonormal decomposition of Y and an eigen, thing of Y. So now induction gives B is equal to, I'll start counting from 2, mu2 V2 x V2, all the way up to mu n Vn x Vn. All of these are real valued, and then all of these are an orthonormal basis of Y. So now we can write A where I add on in my great handwriting. I just append this. Okay, something like that. And I think they're all real valued like before. And then the only additional thing we need to observe is that V1, yeah, was orthonormal to Y to begin with. So it's going to be orthonormal with all of these. Okay, so mu1 will be orthonormal to all the mu2 through mu n because V1 V2 through Vn, because V1 was orthonormal to all of Y, and these were all already orthonormal to each other, so that they're all orthonormal. Okay, and you get an orthonormal basis for the original space. Okay, so we're just doing induction, and you just have to be a little bit careful about once I subtract out that first eigenvectors term, do I really live in the subspace? And then once you live in the subspace, you just do induction. Okay. And then, yeah, once you have this representation, then it's very compelling because it tells you that, okay, every symmetric matrix is your friend. It's a diagonal matrix. That's the key point. Okay. All right. Any questions? Okay, good. So yeah, symmetric matrices, they're your friend. You know everything about them.
Is there a different version of the spectral theorem that states that when you have a symmetric matrix, you just have like an orthogonal basis? Or is this the standard?
Uh, well, this is an orthonormal eigenbasis. I think I just didn't use the word eigenbasis. Oh, so in hindsight, all of those VIs are eigenvectors. Yeah, so you could call it an eigenbasis. I think. Okay, yeah, I know. They're just names. Okay, yeah. Okay, so now what we're going to do is we're going to take the fact that symmetric matrices are very transparent to do this very kind of refined analysis of random walks. Okay. All right, so this crazy thing. Okay, so again, what we're working from a week ago was just simply the fact that there exists a stationary distribution that has the eigenvalue 1, is positive, things like this. Okay, so we are going to also use this because it's a starting point. Okay, so now last time we showed that there is a stationary distribution. It turns out for undirected graphs, we can figure out exactly what the stationary distribution is. Okay, especially when it's connected. The stationary distribution, I don't know if it would be guessable, is going to be the distribution that's proportional to the degrees. Okay, so if the total number of edges is like 200 and you have a degree 5, then it'll be 5 over 400 because the sum of degrees is actually 2 times number of edges. Okay, so here in this notation, I guess W is the sum of all the edge weights. So if you want to take the thing proportional to degrees and normalize it, then you have to do 2 times the total edge weight because the degree counts every edge twice. Okay, so proving this, I think, is not going to be too complex. Okay, we're just basically going to check that this is true because we know there is an eigenvector. We know the stationary distribution is unique, and it's the unique one with eigenvalue 1. So if I can just check that R D is equal to D, then that means D is my eigenvector of eigenvalue 1. Okay. Where's D? Where D is the degrees. Okay, so all right, so we'll just look at RD, and I'll expand that out to AD minus 1D. What is that? D is the diagonal matrix of D.
Square it. Oh,
Okay, just all ones. Yeah, because the diagonal matrix, this is inverting things. So have 1 over the degrees along the diagonals. So then the degrees will cancel out with the reciprocals. You're left with the all ones. And then what's A all ones? It's just counting for each vertex. Now it's a symmetric, right? So it's even the same as the adjacency matrix you're used to. But if I just look at a particular row for a vector, it just has a 1 for every neighbor, right? So if you do all ones going across, then you're just going to count the number of neighbors. You're going to get the degree. Okay, so D is the eigenvector of eigenvalue 1. And then Perron-Frobenius tells you all the rest about being, oh, that's the one, that's unique, that's the right one. The stationary distribution will be proportional to this. I think I have that written out. What a mess. Huh? Okay, so D is the unique eigenvector with eigenvalue 1. Stationary distribution is proportional to D. Yeah.
was not only where we connected.
This is if it's connected. Yeah, just assume it's connected. I maybe you didn't write it down, but if you have two disconnected graphs, then any combination of stationary distribution on the two components will give you another one. So okay. All right, so that'll bring us finally to the theorem that started this lecture. Ultimately, we want to show that we converge to stationary distribution. We even know what that is now. At a rate that's sort of exponential in the spectral gap, gamma. Okay? So it's going to be some eigenvalue analysis. All right, any questions? I think we're going to finish. We might be able to do the Chernoff bound today. Okay. All right. Oh, well, I guess there's some stuff in the way. All right. Someday. Okay. So, we talk a little about some similar matrices. So, A and B are similar if there's some kind of invertible matrix C where A is equal to C minus 1 BC. So, the way to think about invertible linear map is sort of like some map to one vector space to another, but it's invertible, so it's kind of preserving all the structure, right? So C is, you're starting in like the A space, C takes you to a new space, you apply B, and then you kind of map back with C. But at some level, C preserves all information because it's invertible. It's kind of one loose way of thinking about it. Okay, so when you have two matrices that are sort of relatable by an invertible map like this, we call it similar. Okay, and okay, so here's one claim. All right, let A and B be similar. The claim is that C restricts to an isomorphism between the two kernels. What do you mean restricts to? So C originally maps Rn to Rn, and this claims that if I restrict C to just the kernel of A, then this will map kernel of A into kernel of B, and not only that, but it'll be invertible. All right, how do we prove this? Is this even very fun to prove? I don't know. All right, let's let X be in the kernel of A. Let's at least check that it gets mapped to the kernel of B. So I don't know if I define kernel ever. How many people have heard of a kernel? Okay, so I should have defined it. All right, so this is the set of vectors X that map to 0. Okay. All right, so good. All right, so let's say that AX is equal to 0. I want to show that BCX is equal to 0, right? All right, so now BCX is equal to CAC minus 1 CX.
No, it's just CAX.
It will be CAX if you just give me a moment. But if you first substitute in the definition to see where it comes from, you'll get CAX. CACA minus 1x. So these cancel out, and you get CAX. AX is equal to 0. Something like this. And if I had BY is equal to 0, well, you can imagine doing something similar, right? A C minus 1y is equal to, you're going to tell me that I'm wrong, but like that. The C and C minus 1s cancel out. Like that. And you get C minus 1, 0. Okay. All right. Not so exciting. At some level, when we say that C essentially preserves all linear structure, then this shouldn't be too surprising that it also preserves the kernel. Okay, but why do we spend time doing that? Good question. I don't know if this will be a very satisfying. What's going on here? Oh, okay, whatever. Okay. I think there's it doesn't matter. Okay. All right. So the claim is that if A and B are similar, they have the same eigenvalues, and you can use C to map the eigenvectors kind of back and forth while matching the eigenvalues. Why?
Because you just change bases, you don't do anything.
Yeah, well, C is not exactly a change of basis. It is true that morally you can think of C as a change of basis. If C was a rotation, maybe all of these things would be more intuitive. But C is not exactly a rotation. Is that true? Okay, I'm bad at names.
It's like you can change from any basis gamma to beta. There's like a funny notation.
Okay, well, work with me. How can we use the previous lemma to at least show this thing?
You can use a D term.
Okay, I think the trick is just that A minus lambda I is going to be similar to B minus lambda I. Okay, and the eigenvectors are always the kernel, things that get mapped to 0 for various values of lambda. Okay, and C will preserve them. Okay, that's it. Okay, so plug in lambda to be a real eigenvalue, and the kernel will be those eigenvectors for that eigenvalue, and C is mapping them to each other. Good. All right. Okay, so why is that useful? Now, we want to apply the spectral theorem essentially to the random walk matrix. Okay. Why can't we apply the spectral theorem to the random walk matrix? Why isn't it positive semi-definite? It's an undirected graph. So what's wrong? Also, we did the symmetric theorem for symmetric matrices, not necessarily positive semi-definite. So what's wrong with the random walk map of an undirected graph? Why can't I apply the spectral theorem?
Do we know if it's symmetric?
Do we know if it's symmetric? Yeah. It's not symmetric. What would be a nice example of one that's not symmetric?
You just have A to B.
Something like this, A to B to C. So that's like a matrix. A, B, C, A, B, C. So A going to B is 1, 0, 0. B going to A is 1/2, 0, 1/2. C going to B is 1, 0, 0. Oh, that's not symmetric, right?
Yeah.
Okay, good. Well, it's like a symmetric along a vertical and horizontal, but not symmetric in the way we're looking for. Okay, good. So the random walk is not necessarily symmetric. Can anyone think of a condition where it is symmetric? If it's regular, if everyone had the same degree. Can do that for fun at home. Okay, so if a random walk is not symmetric, how the hell are we going to apply the symmetric theorem? Okay, we don't know. Okay, so suppose I took the random walk matrix and I applied d minus 1/2. So that's taking the square root of all the degrees. D minus 1/2 on the left and d to the 1/2 on the right. Okay. Call that the normalized random walk matrix. What's so great about Q?
It's symmetric, isn't it?
That's right. It's symmetric. Okay. And why is Q still useful for us?
As an orthonormal
Uh,
eigenvector.
well, lots of things have orthonormal eigenbases, but why is it going to help us analyze R? Sorry? is similar, so it's going to have the same eigenvalues. So Q is similar to R, but it's symmetric. So Q, we're going to be able to do full surgery and just open everything up, and we'll still be able to say something about R. Oh, geez. Okay, so the spectral theorem applied to Q, right, says that there's some kind of orthonormal basis, V1 to Vn, and eigenvalues mu1 to mu(n), listed from largest to smallest. Now, we know that R's biggest eigenvalue is always 1. So that's why I didn't write mu1 here, so the 1 is omitted. Okay? And meanwhile, we know mu2 through mu(n) is somewhere between the range 1 and -1. Okay? So that we also already know. Okay. All right. Good. So, because the Perron-Frobenius theorem tells us that all of the other eigenvalues are smaller in magnitude to that dominant eigenvalue, which for us is 1. Okay. All right, so now the next question is, what does the first eigenvector look like? How can I try to figure out what the first eigenvector of Q looks like? What are some clues we have? What are some info? So in particular, we know something about the first eigenvector of R. The first eigenvector of R was supposed to be, yeah, when I point at you, the stationary distribution. Yeah. I was watching, everyone seen the movie Moneyball? Whenever he plays the Jonah Hill, it's supposed to say on base percentage. They're not old. They're like 10 years ago. I don't know. Half the age of the Jonas Brothers. Okay. All right. So we know then if you kind of unmap D, V1 is related to the eigenvalues of R by this D to the 1/2, right? We know that this should be proportional uh, to the stationary distribution. And then what do we know about the stationary distribution? What do you know about the stationary distribution of an undirected graph? What was the formula for that? It's proportional to the degrees. Okay, so all I need to know is that V1 to the 1/2 V1 is proportional to D, and that V1 is supposed to be unit length, right? And so you start plugging that in, and okay, that means V1 is supposed to be proportional to square root D, because here I take the D 1/2 and invert it. So you get square root square root of all the degrees. And in here we just normalize it. Okay. So you get something like this. Okay. Yeah, this notation might be a little bit subtle, but this is the L2 norm, right? So all these square root degrees are getting squared by the Euclidean norm, and you get the square root of the whole thing. Okay. All right, so we actually know something about the first eigenvector as well of Q. So it's going to look like this. Okay. So we know the first eigenvector the first term will look something like this, and then you have all these smaller terms, or at least with smaller eigenvalues. Okay, any questions so far? Might have time for the turn-off bound. That I actually have not prepared for. Okay, all right, so now let's go back to proving this thing. Okay. All right, so let's first look at this crazy term. So maybe we'll take a moment to appreciate it. Okay, so I'm looking at some arbitrary starting distribution x, and I'm applying k steps of a random walk, right? We're looking at any graph, and we're applying k steps of a random walk. So however many steps, and somehow we're going to make sense of this, right? But this is utter chaos at this point. Okay, but what can we do? Well, let's just first start substituting in. Okay, so I'm just plugging in this Q stuff. Nothing deep. And so that looks something like this, right? If I just kind of there's no K in the corner there. Looks something like that. Okay. Just repeat it over and over and over again. All right. How can we clean this up? Yeah. Those inner d to the minus 1/2 d to the 1/2 terms, square root d terms, they're going to cancel out. And so that's going to leave us with something that looks like this. Okay. Although it doesn't really seem like we made much progress. We started with r to the k, now you have q to the k with extra d's thrown in. So you shouldn't be that impressed yet. Not that you were ever going to. Okay. All right. All right. But now let's look at q to the k. Right? We know a bit about the structure of q. Okay. All right. So you have all these rank 1 terms, crazy rank 1 terms, and you take them to the kth power. So they're all getting multiplied with each other like crazy. Well, what happens? Okay, so when I take V2 outer product V2 times, say, V3 outer product V3, what do I get? 0. Okay, so V2 outer product V2, V3 outer product V3 is going to get you V2, V3, V2 outer product V3, but this is 0. Okay, so all the cross terms cancel. So then what's left? Every term to the k. Okay, so mu2 to the k, mu n to the k. There's a 1 to the k that's kind of quietly omitted here. Okay, but this is very nice, right? So r to the k seems crazy. You can imagine, I don't know, imagine what the graph looks like if you kind of took all the product k-step blocks, right? The auxiliary graph mapping to RK is some massive dense graph. But here, this is a very nice kind of clean, sparse expression. You did, but there's a 1 here to the k. And this is really just another outer product of unit vectors. It's just, in our case, we can write it out more explicitly. Okay. So this is very nice. It's very easy to understand powers of a diagonal matrix. That's really what's going on, right? Up to some rotation, Q is a diagonal matrix. And it's very easy to understand how a diagonal matrix multiplies. Okay, good. So, right. Oh no. Okay. So now, right. So our goal is to eventually try to analyze this thing. So let me just look at the first term. Okay. See, what do I get here? I guess the square root capital D times square root lowercase d will get you something like d, and the square root lowercase d. Okay, whatever. All right, you're going to get something like this. Yeah, that's how these outer products work. And now, what does the next step look like? It's going to look something like this. That's what the outer product will do. So you'll take the inner product of x and 1s, okay, and send it off in the d direction. Okay, and then what is this? What do we know about x? So it all sums to 1. Okay. All right, so the first term is, all right, and then what is this? It's the stationary distribution. Oh, that's cool. Okay. All right, that's nice. Okay, so now if you plug in what's left is something that looks kind of like this. Okay. And okay, so let's see. Hopefully it's not covered up nicely. Okay, so let's call this, kind of the residual of the normalized random walk. So I kind of ripped out the first eigenvector, and these are the inner directions that are left. Okay, I'll call that S. I know we've used S once, but we're going to use it again just to piss you off. It's because it came soon after Q and R was taken. And so what are the eigenvalues of S? Okay, so what are the eigenvalues of S?
Is it alpha?
Is it what?
The alphas?
0 is one of them now because you removed one of the directions. And then the rest of it is, mu2 to the k, mu n to the k, right? They're all listed right here. You already have S in diagonal form. Okay, so that's so much for S. All right, so you know that S looks something like this. Okay, now we're going to kind of go for the kill. All right, so this is what we're really interested in, right? This is where we are after k steps in a random walk minus the stationary distribution. And based on what we did above, what would go inside here? Maybe I should write rk to the x is this thing, right? And you're subtracting this thing. So what's left is this thing. Something like this. Okay. Making some progress. Okay, now I'm not doing anything special. I'm just expanding out what the norm is, right? It's the inner product of x with itself, the vector with itself. So I have SD minus 1/2 x, dsd minus 1/2 x. I guess I pulled over. So originally I should have written d to the 1/2 and d to the 1/2, and I transposed 1 d to the 1/2 over to the middle. Yeah, that -1 looks wrong. Yeah. These slides have not been proofread. Okay, so I will just jump to there. Okay, now, I want to start trying to upper bound this thing. What can I try to do? We haven't done anything like this before, so it might be hard to guess. Okay, something bounded by a matrix norm. Okay, that sounds nice, although matrix norm is not a word we've used, but it's not far from what we'll actually do. So what is the matrix norm? Since
It's the premium of the norm of ax for all the vectors x.
okay, so what was our definition of an eigenvector for a symmetric matrix? D is symmetric, right? Yeah, XLX, maximizing XLX, right? Overall. So, okay, so that means that this term will be less than equal to whatever's the maximum eigenvalue of D times, sort of that Euclidean length squared of the vectors, right? This is just coming from our definition of eigenvectors and implicitly what matrix norms give you. Okay. But what is the eigenvector, maximum eigenvector of this diagonal matrix D? So D just has a degrees along the diagonal. The largest degree. So if our diagonal matrix eigenvalues are very transparent, right? It's just the biggest entry. That's where delta max is going to come in. Okay, so what will be the next step? Nope. Also, I think this minus 1/2 is going to be a recurring error. Sorry? We're going to move S over. Okay, now what? We're going to do it again. So what is the maximum eigenvalue of S squared? Yeah, so we know all the eigenvalues of S, or at least we've named them. Okay, and then the way I've named them is they were in decreasing order. So mu2 was the biggest in kind of real value, mu n was the smallest. But because you're squaring, you have to be worried about mu n being very negative as well. So it's going to be the maximum of these terms. The omitted terms will always lose to either mu2 or mu n. Mu n could win if it's like a very close to -1 or is -1. Okay, but that's the eigenvectors of S squared. Okay. All right, now what? All right, we're going to move the d over and then do the same thing. So what is the maximum eigenvalue of d to the -1? 1 over what? 1 over delta min. Right, so you're looking at the biggest entry of d minus 1, so that's 1 over the degrees. So the biggest one will correspond to the smallest degree, because that's the smallest denominator. Okay, so now you're going to get delta min. Okay, and then what's the last step? If the x is a distribution, what is its norm? At most 1. Well, how can it get 1? If it has all the mass on one coordinate? Yeah. So if it was like uniform, then it would actually be like 1 over n. Okay, so that's how you get this. All right. Now, to put it back into the terminology of how the theorem was expressed. Okay. All right, so this crazy max term. Okay, I could put the 2 to the k on the outside. Okay. And you probably don't remember. I mean, it's just a name, so it's not that interesting. But this was actually equal to 1 minus gamma. So gamma was measuring what's the difference between 1 and mu2 or -1 and mu n. Okay, so you get this 1 minus gamma to the 2k, which, as you guys have done a million times, is less than equal to e to the minus gamma 2k, right? And not only that, but it's a good approximation when gamma is small. You're not losing much. So you're kind of trying to figure out what's sort of the rate of exponential decay, and it's governed by gamma. Okay, so the spectral gap will tell you how fast it converges. No, we didn't have. Okay, so maybe that's a nice question. So the theorem statement is down here. There's no 2k, and there's a square root. And up here, our analysis, here's maybe a snapshot of our analysis. So how do we get rid of the 2k? Yeah, so we started with the square because then it's nice to expand out the inner product. So we were always analyzing the square difference the whole time. Once you remove that square, then you get 1 minus gamma to the k, square root delta max delta min. Okay, good. Oh, no turn off today. Now, I just want to take a moment. I feel like, obviously we did a lot of math and it is a little algebraic, but what we did, the beginning of what we accomplished is kind of intuitive, right? We were able to analyze a random walk. The bound kind of makes sense. This is some kind of exponential rate of convergence. Okay. And what was very powerful is the fact that random walks, at least up to similarity, are a symmetric matrix. And that lets you very, very transparently break down all the eigenvalues and eigenvectors and make it diagonalizable. Once you make it diagonalizable, it starts getting easier to say, what is this matrix to the 10th power, to the 12th power, to the 15th power? That's what you want when you're analyzing a random walk, because you're applying the matrix 15 times, 20 times, 25 times. So if it wasn't symmetric or wasn't implicitly symmetric, and you didn't have this diagonalizability, you would never be able to get anywhere, right? So that's the key moral of this lecture. All right, thank you. Next time we'll do Chernoff bound.